next session, and now I'll talk about energy efficient process and tools for manufacturing. So in this particular session I'll talk how the energy assessment can be done for a manufacturing process. I will show some examples, but before that I'll discuss about the general framework about how you can one can look at the energy usage in a manufacturing process, because at the end of the day manufacturing is a very energy intensive process. So unless you know that where the energy is being used and what is the energy budget, so that is the first criteria that one needs to know before one can tell, okay, this is the energy intensive process and how I can optimize or modify it. Okay, so again, how do we quantify what is the amount of the energy footprint of a manufacturing is typically given by the carbon footprint. So this is a very popular way. Basically, how much of the greenhouse gas equivalent is being emitted from a manufacturing process. So if we look at the typical greenhouse gas, carbon dioxide, methane, so they are the most prominent greenhouse gases. And for any energy conversion process, there is a cost in terms of the carbon footprint that is being used, and this is typically given in the quantity of kg carbon dioxide. So which means that amount of the carbon dioxide it is assumed to be emitted from that particular process. So this is not only related only to manufacturing, but also in terms of if you are doing any kind of activity. Okay, let's say you are transporting, you are traveling from one location to another, so there is an associated carbon footprint for that. So when you are looking at the manufacturing as a whole, so that is not only about the process, but it is also about the entire the flow chain, basically the entire process starting from the very beginning and ending at the very end. Okay, so what are the typical components in a manufacturing setup? Now if you look, this is a very broad overview. So in the input you have the raw material, you of course need some energy, and then you need to have some tools or equipment which will actually do the manufacturing process. Now if you look at this entire thing, so here you can divide this into process, machine and system. Now process means the basic technique which is at the heart of the manufacturing process, manufacturing technique. Let's say you are you are in a casting environment, and what you are doing is you are melting some metal and you are casting it into some product. Okay, so there the process is the melting of the raw material. Okay, you might be starting with some ores, okay, some form of the raw material. It could be some scrap or some kind of options you get from the ore, and then you melt it. So that there is an energy requirement for that. So that counts as the process. Okay, and for a simple casting, that is quite easy to estimate the amount of the energy requirement for a process. Let's say you want to make a cylinder, right? If you want to make, so amount of energy to make this cylinder, okay, so amount of energy, first you need to take it to a molten state, right? So how much energy would you need to take it to the molten state? So that is nothing but, you can write okay, so this is a simple energy equation. You take it from the room temperature up to the melting point, and then you give it the latent heat of fusion. Okay, so if you can calculate, given the volume of the part that you are planning to make, so this is the energy that is needed. Okay, now this will give you some amount of, let's say, kilojoule. Okay, depending on the material properties, depending on the size of the product that you are making. But in an actual scenario, if you have only this amount of the energy, will it be sufficient to make the entire manufacturing process, manufacturing setup? Because this is only the theoretical consideration, okay? But on top of that, you need to have some auxiliary machines, you need to have some considerations for the entire process workflow. Okay, so this equation only deals with the process, okay, but you have a machine, okay. So in order to operate this, you need to have let's say a furnace, okay. Now the furnace itself will you need to take the temperature from the base to the high temperature point, and you need to keep it at that point. So that itself will require a lot of the energy, which is not accounted for in the process calculation. So if you want to calculate the entire footprint of a manufacturing setup, you also need to include the machine aspect, okay. Similarly, there is the system. Now system means which goes beyond the machine part, okay. For example, you need to have the raw material, you need to bring the raw material from some port, there is the transportation involved in that. So what is the energy requirement for that? Because if you are running a plant, you also need to account for that. Let's say you tell the power station that I need this much energy for to operate my plant. So you have to calculate all these things, then only you will be able to give a predictive number to the substation, okay. So now system here includes the transportation, it also includes the energy which is required for making the component or the tools, okay. Let's say you have a furnace. Now the furnace is probably built by some other company, you are getting the furnace there. There is also energy associated for making that component, right? So where does this come into the picture? So yeah, so here if you look, we can broadly divide them into three sections, and you take the energy, material and tools as the input, and finally the product is what you want. But this is the carbon footprint is something that you cannot avoid, and it kind of is a byproduct of the entire process, okay. So now we need to see what is the carbon footprint for a how one can develop a framework for that. Okay, so this table again tells you that okay, there are the three components: process, machine and system. The process is related to the physical understanding of the process, and you need to consider the raw material, the process energy, process time in order to get an estimate. For a machine tool, there is a lot of additional things. For example, you need to have some coolant pumps. If you are doing a machining operation, okay, you need to run the spindle, okay, you need to move it in the x and y direction. You need to turn on the coolant, you need to turn on the chiller, okay. So there are a lot of peripheral things which needs to be taken into account. There will be some ventilation effects, okay. And then you also need to think about the starting time, downtime, idle time. All of these things will come into the picture, and what is found is that these things actually require a lot of additional energy, lot of extra energy compared to the process itself. The process might take 10 minutes, okay, but you need to start the machine, you need to bring it to a stable state, you need to give it some idle time to run. So that entire flow takes a lot of energy. And then finally you have the system, and as I mentioned, the system is related to the overall production line, starting from the beginning and finally at the end. So when you are assessing the energy footprint of a given process, you should start from cradle to gate at least, which means you are starting from the energy required for generation of the raw materials, transporting, and finally you are ending at the phase where the product is out in your hand, okay. So that will give you the total energy component, and then these are all the things that you have to take into account when you are looking at the system level. Okay. So now let's look at the process level. What happens at the process level? The process level is very simple. That comes from the physical understanding of the core process. Okay, and you can calculate what is the energy requirement. For a casting, you can calculate by this method. Okay, for example, for a machining, you can also calculate what is the force which is being required, and from the force knowledge, the feed rate knowledge, you can calculate what is the power, and from the power you can calculate what is the energy. Okay, so it depends on the the final product geometry, material properties, everything. Now there is a carbon emission factor which depends on what is the source that you have used to generate this energy. So for example, if you have used a fossil fuel, then this carbon emission factor from the source will have some particular value. If you are generating the energy from renewables, then this will have some different value. Okay, and you combine these two, and finally you get the process carbon emission. Okay, so this is the process energy, this is the carbon emission factor for the source, and then finally you get the process carbon emission. Okay. Now you can now in order to calculate this process, we look at that you can actually develop some mathematical models or equations, and that will give you some rough idea of the what is the process energy that is required for a given manufacturing setup. Okay, so now at the machine level, in the machine level, the first component is always there, the process carbon emission. Okay, so that is the core of the manufacturing technique. Now you will have auxiliary carbon emission, that that is coming from the auxiliary machines which are running, the ventilation, the chillers, okay, the motor movement, all of those things. Tool usage. So here also you will have, let's say you are running a laser based machine. So when you are running the laser itself is a tool. So there will be some carbon emission related to that. Or if you are running a machining operation, the tool itself is a drill bit or a end mill. So there is a like tool usage carbon emission that also needs to be taken into account. And finally there will be the consumable. Okay, so you have some workpiece. Okay, you want to machine it. The tool itself will undergo some wear and tear. But in addition, you might need to use some coolant. So that is a consumable here. You are using some coolant, how the coolant was manufactured, how the coolant was prepared. So there is some carbon emission related to that. Okay, or if you are doing some, let's say, laser welding. So in addition to the workpiece, you might need to have some shielding gas. So that will be the consumable in this case. So now you can calculate the overall machine carbon emission, and you can sum the components for each of the parts, and you can have an estimate of the overall machine carbon emission. And you can in terms of the energy, you can expand this, and you can get this kind of equation. So this is just we are expanding each one of these terms. Okay. And you can have multiple types of the consumable depending on the quantity, depending on the process that you are doing, and you can have an estimate for the machine. Okay, now you go to the system level. As I mentioned that in the system level, what you have here is that first of all the carbon emission at the machine level, then you can get the concept from the transport, how much energy it is required for transportation of the raw materials. Now this is not only for the raw materials, but it also could be transport for the finished good. Okay, and sometimes if you fail to account for that, that itself can be a very that itself can be a very big contribution for the energy. For example, let's say you are making some ice cream. Okay, you have the process ready for that. Now the finished product, if you want to transport it to some other location, you need to have a cold chain. So the carbon emission from the transport in that case will be quite significant, okay, because you need to maintain the cold chain, okay. So that is sometimes, a lot of the, it takes a significant chunk of the carbon footprint. And production means I am talking about the production of the raw materials, production of the tools, production of the consumables, and the disposal. Okay, so in many cases, if you are not, if you are just considering about the take, make, waste, considerations, you are not even considering what is the carbon emission for disposal. You throw it in the dustbin and you do not care. But this will also have some, very vital role to play if you are looking at the entire carbon footprint, starting from the cradle to the grave. Okay, you are now looking from cradle to the grave, not from cradle to the gate. Okay, so gate means when the product is out in the hands of the consumer, that is up to the gate. But now the consumer uses it, consumer spends some energy, the consumer disposes it, and then that is the cradle to the grave. So there will be some carbon emission for that as well. And overall, you can estimate what is the typical system level carbon emission for a given manufacturing component. So if you are considering a plant, then all of these things will be needs to be taken it into account. Okay, so you can basically, this is the system. You can split all the individual components into their the subcomponents, and you can write an equation like this. Okay, now yes. It is Q is the quantity. Okay, if you have multiple amounts of consumable, what is the quantity for each consumable? Okay, so you let's say you might need 2 or 3 different types of consumable at different quantity. So you need to multiply each one of these and then add them. Okay. Okay, so now here you see that in this equation you have the term which is the T life for a particular component. So which is basically the lifetime of the component. Now if you want to reduce the carbon emission for a system, you need to increase this lifetime. Okay, so if you increase this value, the overall carbon emission will go down. So one of the easiest way to decrease the carbon emission is to try to increase the lifetime. Okay, so let's say if you are running a component for 100 hours, if you are able to find a way to run it for 1000 hours, that itself will you do not even need to do anything else. That itself will cause a drastic reduction in the carbon emission per component. Okay, so that is why like when we listen to Professor Takata about the life cycle managements. So that is why it is also very important to consider the lifetime. That will have a direct relation with the carbon emission for that particular process. So there are some typical tools and methods for energy assessment. Again, these are I'm not going to go into details, but typically there are some ISO standards which particularly industries or production plants they need to follow, and these kind of standard basically gives a guideline or the framework that particular industry or particular production plant will need to production plant can use in order to assess their energy requirement. So this is how it can be broadly differentiated, like what are the different ways for the energy assessment. So one of the ways to just do a basic energy analysis. Okay, so you have to look at what is the energy in and energy out, and that can be based on energy audit or energy benchmarking. Energy evaluation, you can develop some statistical models or some mathematical or process models that will give you an idea about the the energy evaluation, the energy that is being needed for a particular process. And eventually all of these relates to the energy saving measures, because it is not only sufficient to do the energy analysis and evaluation, you also need to see how we can optimize the process so that you can save more energy. So now what do you mean by, if we look at the energy analysis methods, so typically energy audit, which is basically you see, okay, you have a plant, what is the typical energy usage at the beginning of your day, for example, and what is the energy usage at the end of the day. So based on the utility bills, or if you know the specifications of the machine parameters, then you can have a rough estimate. Okay, and you can use this to know that, okay, this is the most energy consuming process. Another way of doing this is energy benchmarking. So here what happens is, basically, if you want to compare how efficient is your process or plant, you look into the existing literature or existing benchmarks, and then you compare how well you are placed against them. Okay, for some of the values, if you do not know, if it is difficult to calculate, you can get those values from the benchmarking that is typically available in the literature. Okay, so for example, if you are running a system, typically the manufacturer will tell you, okay, if you run the system for this many hours, this will be the energy output. Today if you see that all of the home appliances, they come with energy rating. So the manufacturer gives you already that information that, okay, this is the kilowatt hour that this machine will use. So that is basically based on the energy benchmarking. So that can also be one of the methods and tools for the energy assessment. Now when you are talking about the energy evaluation method, so that typically goes into a little bit more deep. You try to analyze how the energy is getting consumed and from where the major consumption is coming. So for that, either you can develop some tools. Okay, it could be some mathematical tools, it could be some statistical tools, or you could use even some kind of sensors. Okay, let's say you want to know what is the energy usage for a simple cutting process. Okay, one way to do is you put some sensors. You can put some load cells in the turning machine, and you calculate what is the force for in each of the components. Okay, now if you know the force in each of the components, you can come up with some mathematical ways to calculate what is the energy requirement for a given given operation. Okay, so that is the energy evaluation. And today with the use of a lot of sensors which are available to us, you can easily get a lot of information from the machine itself. Okay, so you do not necessarily need to rely on the manufacturer's specification, but you can do your own evaluation by these mathematical models. And finally, you need to, once you know the energy usage for the different parts or different processes of a manufacturing system, you can now try to use some data-driven techniques or some system modeling approaches to know in which zone or in which location most of my energy is being used, and then you can try to optimize that. So here the primary focus is on the energy saving measures. Okay, so now I will give you two examples. So these are based on the work which was done at IIT Hyderabad by Professor Reddy and Professor Surya. So I will show you that how these two techniques, how it can be used to do the energy assessment and finally come at an optimized process parameter design to reduce the energy usage. Okay, so this is based on the double-sided incremental forming. So yesterday or day before yesterday, Professor Reddy gave a very brief about that. So typically what it means is that this is a, if you want to make a component by forming, this is the traditional method. Okay, you have a die, you have a punch, you have a sheet, and you use the die and the punch to deform the material. Okay, the problem here is that you need to make a die and punch every time when you are changing the component, the geometry of the component. So another way for doing this is double-sided incremental forming, where you have the sheet and you have a tool. The tool will deform the sheet and it will give the required geometry component that you want to make. Okay. So this starts with a CAD model. From the CAD model you generate the tool path, and then you can finally get the components, and you can make very complicated components using this method. You do not need a separate die and punch for this. So for this process we will look at the energy assessment perspective, how you can calculate what is the energy required to run this entire manufacturing technique. So now let's look at this. So total energy consumption by the machine. So we call it as E total. Now what it will consist of? So one is the standby part, which is the energy like the controller, fans, lights. If you are starting on the machine, there will be some base level energy usage. You cannot avoid that. Next is the variable part. Now the variable part is depending on the tool that you are, depending on the component that you are going to make. If you want to make a small component, this energy requirement will be less. If you want to make a big component, this energy will be more. Now this variable has two parts. One is the energy free traverse, energy deformation. Okay, so how a typical the double-sided incremental forming works is that there is a tool. The tool needs to traverse in two directions, and depending on the geometry, it will deform the material at some locations. Okay, so the free traverse is the energy required for the transformation of the tool when there is no deformation happening, and energy of the deformation is the energy which is needed for the plastic deformation of the material. Okay, so you can sum all these and you can get the total energy. Now if you want to know what is the standby, the only method is to you turn the machine on, let it come to a standby level, and then you calculate what is the energy usage for that. Okay, now we also need to calculate what is the energy for the free traverse and what is the energy for the deformation. Now you can as you can imagine that the energy for the free traverse, it will be related to how fast you are moving. So typically it has some screw nut mechanism. So you give some torque to the screw, and then it will the motors will move in the linear direction in either X or Y, and that will give you the energy of the free traverse. And for the deformation energy, again we can do some fundamental stress analysis calculation that will give you what is the energy required for the deformation of the workpiece. Okay, so for example, if you know the stress levels at each point, and if you know the geometry of the energy, then you can calculate the work done per unit volume, and then you can multiply it with the feed rate, and that will give you the energy per unit time. Okay, so in this way you can estimate what will be the total energy requirement. So you can develop some mathematical models for these two. For the standby, you have to rely on the experimental data, and for the free traverse and deformation, you can develop some mathematical models. Now this is typical experimental method. Now this is you have a power meter which you plug to the machine, which will tell you okay what is the total power usage in a given time. And for the free traverse, you basically use the power meter to experimentally calculate what is the reading shown by the power meter at the start and what is at the end, and that difference will give you the energy which is required for the tool to traverse. Similarly, for the if you want to calculate the deformation energy, then what you need to do is your tool is moving and at the same time is it deforming. So you can get the energy when the deformation is happening as the energy at the start and the reading at the end, and the difference of these two will give you the deformation energy. Okay.
So which sheet
Sorry?
energy which sheet I got?
Yeah. So energy free traverse. Let's say this is a component that you are trying to deform, and you have a tool like this. Okay, so when the tool is traversing without any deformation to the plate, that is known as the energy free traverse. Okay, now the tool is engaged with the workpiece, it is moving in a given direction, and simultaneously the tool is moving as well as the energy of the plastic energy for the deformation is taking place. So both of them are measured by the machine, measured by the power meter at the same time. Okay, so that is what we mean by the that is what we mean with this term energy width sheet. Okay, when the tool is moving as well as the deformation is happening. Now if you want to know what is the energy only for the deformation, you have to subtract these two.
The free traverse is basically just the machine moving.
Yes.
Without deformation.
Without deformation, yeah. Okay? Okay. Now here is a mathematical model which will help you in calculating what is the deformation energy. So for that you need to know the geometry of the component that you are trying to make. You need to know the process parameters. Okay, from there you can calculate the tool path and the time required for making it. Okay, now from here you can calculate the stress and the strain. You can do some finite element analysis. You can calculate what will be the force in different directions, and if you know the forces, you can then get the power by multiplying the forces with the feed rate. Okay, so force times velocity gives you the power. Okay, so here you can get the deformation power. Now you know the deformation time, so you can get the deformation energy. Okay, you multiply the power by the time and then you can get the energy. Yes.
Previous slide, there is a leading sheet, right? That's in the sheet.
Yes.
Which is actually a deformation energy.
So this includes both deformation and the energy required for the traveling of the tools. Both of them are included in this term. So energy width sheet. So when the sheet is getting deformed, the tool is also moving. Right? It cannot happen independently. The tool always has to move when the sheet is getting deformed. So the energy width sheet includes both the effect. Okay, the energy associated for the movement of the tool as well as for the deformation energy.
The moment we can say free traverse, right? We get reach to sheet.
Yes.
Free traverse.
Yeah.
But normally we are calculating.
Free traverse is the one when the tool is not engaged. Yes. Okay, but when it is getting engaged, then the tool is still moving. But now there is an additional energy for the plastic deformation. Okay. Okay, so now this formulation will give you a way to calculate the deformation energy. Now, so once you can calculate the deformation energy and you can try to validate your model with the experimental results. So this is some of the validation results. So there are several geometries which it was formed. So let's say you want to make an ellipse. and this is how the tool is going to move. Okay, and this is the total power which has been measured by the power meter with respect to time. Okay, and if your model is if you are developing a model properly, then you can see that there is a good correlation between the theoretical value and the experimental value. Okay, so similarly, with different type of geometry, you can see that the model kind of gives a very good estimation. Okay, so which means that even before you do the processing, you can know that, okay, this is the amount of the energy that will be required for this particular geometry. Okay, so this is the energy assessment stage. Okay, you can assess what is the energy that is going to be required if I want to make this component. Now the question is how you can optimize. Let's say for a given component here, you know that this is the power profile. You can calculate the area under the curve that will tell you the energy. Okay, so for a given component, you know that this is the energy that is required. Then how you can optimize that, how you can try to make it less. So one of the way to do this is by selection of the optimal orientation. Okay, if you have a part, if you just change the orientation of the part, if you make it vertical from horizontal, then it has been found that there is a significant change in the energy consumption. So here, let's say this is a complicated component, you are trying to make it. Okay, now you see this angle theta is the orientation angle. Now this graph tells you what is the energy as you are changing the orientation angle. Okay, if you change the orientation angle, your energy requirement is also changing significantly. And this is because when the tool traverses in, let's say, in this direction versus in this direction, the energy requirement is different. Okay, in this direction, the tool has to counter the effect of gravity. So the energy requirement in traveling in the z direction is typically more compared to that of traveling in the horizontal direction. So when you are changing the orientation, you are able to play such that your energy requirement is less if you just orient the geometry of the tool. Okay, now here you see that this is a very interesting result here. The energy for the free traverse is almost 3000 kilojoules, but the plastic energy of deformation is only 15 to 16 kilojoules. So which means that the most of the energy is coming from the machine itself, because you need to move the axis of the machine. Okay, so it is not coming from the process. Okay, so if you just tell that, okay, manufacturing is only related to the process, but if you ignore the effect of the machine tools, it will be grossly underestimating the amount of the energy that is being required. Okay, so one needs to consider these holistically when you are comparing, when you are doing the energy assessment. Okay, and by proper judicious orientation, it is possible to significantly play with the total amount of energy that is required. Okay, so now another example that I am going to show is based on the powder bed fusion, and this was also done at IIT Hyderabad by Professor Surya Kumar and Professor Reddy. Okay, so now when you are doing additive manufacturing process, so typically it is the process is the heart of the manufacturing. You put some energy, you get the part of a given mass, and there might be some scraps. Okay, so this is only the energy for the AM production part, but there is a significant steps which are going before and after that. Okay, so before the AM part, there is a pre-production part where you have to generate the metal powder through gas atomization. That will require a significant energy, or you are doing a metal wire, using a metal wire as the raw material. That requires even more energy because you have to do hot rolling, you have to do wire drawing. So those steps will require significant amount of energy, which also needs to be taken into account. Similarly, after the post production, the part you built on a flat substrate. Okay, now you have to separate the part. You have to do some some part separation machining. So that will require some energy, and sometimes you also might need to do some finish machining. Okay, that also sometimes requires a lot of energy. So the total energy is, one should be looking it into when you are just doing any additive manufacturing. So the energy for the additive manufacturing should not only be considered only for this term, but also for the other energy terms. Okay, so here this table shows typical the energy assessment at different stages of the manufacturing, at pre-production, during the additive manufacturing, and finally by the post-production. Okay, for different types of the processes, for direct energy deposition and powder bed fusion. So here we see that the energy required for the production of a wire is typically more than energy required for the production of a powder. Okay, because for the production of wire you need two steps. You need to do the rolling and then you need to do the wire drawing. For the powder it is typically one step, gas atomization. Now if you look at this one, okay, you see that the WAM process, WAM is the wire arc additive manufacturing. So it basically uses a welding torch to do the to build the material layer by layer. So in this case you have an arc which is generated, and that typically requires lower amount of energy compared to whether you are using a laser based process, for example. Okay, because inherently when you are using a laser, or when you are using a electron beam, the efficiency coming from the wall to the laser output is typically quite poor. Okay, let's say if you are drawing 1 kilowatt of power, your laser output might only be 30 watt. Okay, so that is called as the wall plug efficiency. So wall plug efficiency is typically quite less for laser or electron beam, and that is why they require more energy to do the same processing. Okay, now among the laser, now if you look at the AM production part here, it is if you look at the EBM here consumes the lower amount of energy. Okay, this one compared to that of these techniques. Now this again relates to the absorptivity of the laser. So typically when you have a laser and which is shining on a material, the absorptivity plays a big role. If the material is highly absorptive, then you will require less amount of energy. So for electron beam, typically the absorptivity is more compared to that of the laser. So with EBM the energy requirement is less. Okay, now for this process again sometimes it also depends on the specific energy consumption depending on the given material, and there is a wide range for this lens process, laser engineered net shaping. And for the post production, you see that these PBF typically requires less amount of energy because the surface finish is better in powder bed fusion compared to that of the DED. Okay, so at each stage you can do the energy assessment, and which will give you an idea, okay, which process is more energy efficient. Now this graph basically shows the same thing. So here what we can see that, typically it says that for a lens process the energy requirement for the additive manufacturing is quite high, okay, and for VAM it is quite less. In most of the cases, most of the energy is here coming from the metal AM process, okay. Okay, so how to then do the analysis for this? Now this is a very complicated formula. We will not go into the details, but basically, for each of these steps you can calculate what is the energy for that. Okay, so for example, this is a step where the hatching is happening. When the laser is moving to fill the internal area. So that will be given by some equation. Okay, so formulating the equation, it is not as challenging as finding the value of some of these, power components. Okay, so if you have an equation which you develop, but now if you want to use it, you need to find out what is the power value. Okay. So the challenge here is to able to find the subcomponent values. Okay, so here this is the setup. So here also you use the same energy meter that will give you the power information for each step. Okay, and this is the energy meter is plugged to the back of a laser powder bed fusion machine. Okay, so this graph typically shows the power versus time for a typical operation of a laser bed fusion. So it gives you the energy differentiation or the energy budget for different activities which are going on. So here you have the ideal power consumption. Okay, so that that takes up a significant chunk. If you turn on the machine, this is the minimum energy that you have to use. Then you turn on the ventilation fan, that requires a lot of energy. Okay, next you turn on the laser unit, but you are not running it in the exposure mode, you just turned it on. That requires some energy. Okay, next is when you are moving the powder bed, when you are moving the motors, that requires some amount of energy which is given by this amount. This component here is when the laser is actually operating, when the laser is on and you are actually doing the additive manufacturing. So this is the energy component, and if you run the chiller unit to cool it down, the chiller unit takes a huge amount of energy. So the thing here is that laser unit, if you look at, this is the laser unit consumption. This is almost similar to the ideal power consumption or the consumption of the ventilation fan. Okay, so if you call that this is the process energy, the machine energy is as big as this or sometimes even greater than this. Okay, so the total energy to run the machine is quite huge. Okay, the total the actual process energy might be quite not so significant. Okay, and this graph here shows that how the energy energy reading changes when you are doing separate operations. Okay, so this is the base operation. When you are turning on the laser, it jumps up. When you are turning on the chiller, it again jumps up. Okay, so basically from this graph you can calculate what is the energy for each step. Okay, so from this graph it is clear that if you want to, you cannot avoid these components, the ideal power consumption or the ventilation. So if you want to maximize the usage, how will you do? If you want to make a small part, okay, then you still need to account for these components. Okay, these you cannot avoid, or you cannot even make it less. So you want to maximize the capacity utilization. So let's say if you want to make one part, okay, even for making only one part you need to turn on the machine. The machine itself will require a lot of energy. you need to turn on the laser unit, that you need to turn on the chiller unit, that all of these things will require a lot of energy. But if you make 4 parts, then the process energy will be increasing, but the constant standby energy, they will be same, right? So what it means is that the total energy required for a given part will be less. Okay, so if you want to maximize the capacity utilization, you ensure that you try to fill the as much area as you can. Okay, so if you want, rather than making only one part, you wait and see when you have multiple parts to make, then only you turn the machine on and you run the system. Okay, so this is the energy requirement, total energy consumption per part. Okay, when you are making a single part, it is this much amount of megajoule you are using. If you are using 4 parts, it reduces significantly. Okay, so even though the process energy itself is increasing. Okay, even if you consider that, okay, when you make these 4 parts, you need to use a separate post-processing step. You need to cut it down to get the individual components. So that will require also some energy. But even if you consider that, then also building with 4 parts is much better, right, compared to building with the single part. Okay, so if you want to maximize the capacity utilization, you try to fill the area as much as possible. Okay, before running the machine on. Okay, so yeah, now another part is you want to make this component. You can make this component either horizontally or you can make this component either vertically, which will be better. So you see here, this is the component which is built. This is the base plate and this is the part which you are building by the powder bed fusion. Okay, now the same component, you make it in the Z direction or you make it in the Y direction. Okay, now when you are making it in the Z direction, so this will have many more number of layers. Okay, when you are making it in the Y direction, you have less number of layers. Okay, now between this and this, it has been found that when you increase the number of layers, the amount of the energy consumption is increasing. Okay, so if you want to make the same cuboid geometry, you ensure you orient it properly so that the energy consumption is less. Now this is for a very simple geometry. If you have, let's say, complicated geometry, then you need to do the calculation which will be my preferred orientation. Okay, so you can do the orientation optimization to find the best method for best orientation for minimizing the energy usage. Okay, so these are the results that you can see when you are making it in the Z direction. The total energy consumption is quite high. When you are making it in the Y direction, the energy consumption is less. Okay, even though if you look at this pie chart, okay, so the ideal energy percentage is given by the red one, so that is more or less similar. Okay, so that in terms of the ratio wise, it is similar, but when you are moving in the Z direction, the number of layers is more, so that causes more number of energy intensive turns. Okay, yeah, so these are the observations, like 46% energy reduction is observed when you orient it in the Y direction, even though the energy consumption of the laser unit is similar. So the additional energy is typically coming because of the here. Okay, so this step is using more energy, so basically it is taking more time to run the setup. Okay, so in summary, what I'd like to just conclude is that So, if you want to know the carbon footprint of any manufacturing process, you need to do a detailed energy analysis, and that should not only include the core process, but it should also include the machine. It should also include the entire workflow, the entire supply chain, the route of the production. Okay, because much of the energy usage also happens there. So it is not only necessary to optimize the process parameters, but you also need to optimize the machine parameters. Okay. So yeah, energy consumption happens at the process, machine and the system level, and so appropriate methods must be used. Okay, it can be a lot of techniques. Yeah, one can make energy audit, one can make energy benchmarking, or one can develop some tools or some mathematical models which can help in predicting the amount of energy. So as examples, we show that judicious energy analysis studies, it can drastically affect and reduce the energy usage. And one example was shown by giving the effect, the orientation effect, both for the forming and for the additive manufacturing. If you are able to orient the part properly, you can significantly reduce the amount of energy. So with that, I'd like to thank you. Yeah.
Apart from the information and like orientation, like one more point I would like to add is the power factor.
Mm-hmm.
So during the whole process of manufacturing, when you observe the power factor, and if the power factor is increased maybe because of the fluctuation within the process, or there is some flux loss
Yes.
because of the irregular shaping, or maybe when you are creating a certain shape, some additional part is getting generated which is useless.
Yes.
So you can also observe from the power factor, and power factor correction can also be done to reduce the energy consumption.
Yes, yes, definitely. So for additive manufacturing, for example, sometimes when you make a part, there will be some support structures. Okay, if you want to make a hanging part, you cannot make hanging part. You need to make some support structure. So that support structure will, it will be discarded at a later stage. But that will require a lot of energy, not only while making it, but also while discarding it, while doing the post processing. So that is also one needs to take into account, right? How to minimize the additional discarded parts. How to minimize that? Yeah.
And even so the mode of power, when we use this copper armor wires instead of aluminum armor wires, so mode also plays a very important role in increasing and decreasing the
Yes, definitely. The material property is the fundamental thing. When you change the material, so even if we talk about the, because let's say you are using a different material, the material properties will be different. Okay, the mechanical properties or the thermal properties. So that will directly affect the process energy. Okay, so the first consideration is the material that you are using.
So it's basically a holistic approach.
Exactly.
Rather than just the orientation, it's the what kind of even the source of power.
Yes.
From the source of power to the material selection to the shape you're selecting to form a shape. So it's a process when you observe the energy utilization.
Definitely, yes. So it.
Carbon footprint.
Yes, yeah, definitely. I mean, so these orientation studies were done considering the same material and the same process. But if you want to look at the entire chain, you have to look at for example, here. If you want to, this is you are making by additive manufacturing. If you want to make this by machining, okay, then you need to consider what is the energy usage for the machining process, and that will depend on the type of the material that you are using, right? So it is starting from the material selection, the process selection, and the process parameter selection. All of these will eventually basically tell you, okay, this is the best process to choose. Yeah. Yeah.
The deformation energy calculations.
Yes.
Statement, right?
Yes.
You said that the deformation energy is the difference between energy of with the sheet and energy of retransmission.
Yes.
Energy of free transfers is in transfer directions, but
No.
energy with sheet is the energy of the pool and also plastic pool.
Yes.
But the pool is not moving in a transverse direction. But
No. Energy of the free traverse. It's not transverse. Traverse means when the tool is moving either in the horizontal direction or in the vertical direction. It can move in any direction, but it is not engaged with the workpiece. So let's say this is the deformation, this is the plate, and this is the tool that you are trying to deform. If the tool is moving, without engaging with the workpiece, that is the energy of the free traverse. Okay, now the tool comes and engages with the workpiece. It is giving a force that will cause a plastic deformation. Okay, now it is giving the force and then it's still moving. So
the depth of free traverse and the depth with the sheet is also same. Whatever the tool moving.
yes, so the tool is also moving. I mean, when the plastic deformation is happening, it is not independent of the tool motion. Okay, so while with the experimentally while you are measuring that, you cannot differentiate that. Okay, experimentally you have a power meter. The power meter only gives you initial and final reading. It does not know what is the process which is happening. Okay, so first you know that, okay, if you want to move the tool by this much, this is the amount of energy required. Now you bring this tool, you engage with the workpiece, you move by the same amount. Then the additional energy is because of the plastic deformation energy. Okay.
So, what is the equipment used for power meter?
So this is in-house built equipment. So you can get these kind of energy meters also commercially. If you are asking for the exact model, then I suggest you to look in the references. Yeah, any questions? Okay, so if not, then we will conclude the session here, and we'll now break for lunch, and at 2 o'clock we will be again resuming the participants' activity. Okay, thank you.